Hi again, and welcome back to Lecture 9, the second and last one about early type galaxies. As usual, this one comes in 3 parts. The first 2 parts are both about the mass distribution inside early type galaxies and how we can infer it from observations. And in the last part, we are going to revisit scaling relations, this time, of course, with a focus on early type galaxies. The reason why we have 2 different videos, 2 different lectures about the mass distribution is that the second part is about gravitational lensing, which is actually a topic that is way larger and goes way beyond just the mass distribution in early type galaxies. So I thought that deserved to get a video and a part lecture of its own. But first, we're going to go into the mass distribution in early type galaxies from stellar dynamics and from hot X-ray gas. In stellar dynamics, what we do is that we look at how the stars are moving around in the gravitational potential of the galaxy and trying to use that to infer the shape, the depth, and kind of the steepness of this gravitational potential, and in that way infer the distribution of mass inside it. We do this by 2 models, as you can see, or 2 methods, as you can see here. The first one being about the virial theorem, and the second one being from dynamical modeling. The virial theorem is kind of a coarser, more primitive version than the one with dynamical modeling, but it's often also the only one that we really have access to observationally, because dynamical modeling is observationally oftentimes a good deal more expensive, more demanding. So when we have access to sufficiently good observations to do the dynamical modeling, we might do that, but oftentimes the virial method is all we really can do. So what we do is that we write up the virial theorem. The virial theorem states that 2 times the kinetic energy perfectly balances the gravitational potential energy under the assumption of equilibrium. Gravitational potential energy is the thing we want to map, right? And the kinetic energy is the one we will then be attempting to capture first and use as a way to mapping the gravitational potential. But this is not so easy because we do not know exactly how we can mathematically formulate this. Like if we were going to do this like absolutely completely correct, we would have to basically map the mass and the velocity of every single star in a galaxy potentially millions of light years away, and obviously we cannot do that. So what we can do is that we do this little hack where we write the kinetic energy as the usual classical mechanical version of kinetic energy as half times the mass times the velocity squared, but where the mass is this weird thing here we call the virial mass, and the velocity squared is replaced by the velocity dispersion squared, or rather the virial velocity dispersion squared. And the thing about these 2 things is that we do not know exactly how they relate to actual velocity dispersion and actual mass, or what mass it is. We know they have dimensions of mass and velocity, or velocity squared. And we also know that they together work in the same way as mass and velocity in this equation, this force balance equations that we're having here, or rather energy balance equation. Also, we do the same thing with the gravitational potential energy, where we write that in the usual way, but replace the height and the mass squared with this virial mass from before, and this radius rg, which is called the gravitational radius. Again, we do not know exactly what these mean. We know that they are of they are a kind of radius and a kind of mass, but exactly how they relate to the actual mass and the actual and what radius it is as of yet unclear. But what we can do then is that using this equation here and these two formulations, we can equate these two right sides, and we get this expression that we have here, where we get that the virial mass equals the gravitational radius times the virial velocity dispersion squared divided by the gravitational potential, the gravitational constant. And what we do now is that, again, we have this radius Rg, which is the gravitational radius, and the virial velocity dispersion here, that we don't know exactly what they are. But we know that they're kind of sort of the velocity dispersion, and it is a radius. So what we do is that we rewrite this expression to be the effective radius of the galaxy times the central velocity dispersion squared instead of these other sizes, and then times a coefficient that we call the virial coefficient here. And this is basically a coefficient that just encodes our ignorance about these two things over here, right? So we throw all the stuff we don't know about these things over into this mystery number we call the virial coefficient, and then we can express the rest in terms of well-known old friends, the central velocity dispersion and the effective radius. These are things that we do know how to deal with, unlike the gravitational radius and the virial velocity dispersion from before. So basically the virial coefficient, again, is something that encodes our ignorance. And we can then try and start hunting for that, for a correct value of that, which is something we can do. We can sort of calibrate this number by looking at nearby galaxies that are well studied, that we know really well. And what we have found is that a typical number is just about 5. And so we define this number that we call the dynamical mass as the virial mass in the case where the virial coefficient is equal to 5. So the dynamical mass is something that is rather easy to measure and is rather easy to report and compare directly to other such studies in the literature. And so when somebody has reported a dynamical mass, what we basically have said is that under the assumption that the system has a virial coefficient of 5, the virial mass that we have measured is so-and-so. In some other cases where we have better observations at our disposal, we will turn to dynamical modeling, which gives a spatial mass density distribution. The virial theorem will basically just give us one number, right? It will give us the mass based on some observations, but it will not give us a value or a distribution of how the mass is distributed internally in the galaxy. Dynamical modeling can do that. But this requires us to be able to measure the velocity dispersion and so on in many, many different positions in the galaxy. So it requires us to, it requires us to be able to measure the velocity dispersion and at a large number of positions inside the galaxy. So it is more complicated to do the measurements, but we can also get a more detailed result out of it. So the method is described in more detail in the book, and I will ask you to refer to the book for a better, more detailed understanding of what is going on. But what we basically do, kind of to outline it, is that if we assume spherical symmetry, then we get what's called the Jeans equation, which tells us that at a given radius, and this is a projected radius seen from our position, a projected radius from the center of the galaxy. The velocity dispersion along the line of sight at this projected radius squared is given by this formula here, where the first thing we have here is the surface density of a tracer population of stars that we use to perform this measurement. And then we have this formula that shows us here what is called the anisotropy parameter. I'm going to come back to that one. And the projected radius over the real radius, and then the actual real density at this position, at this radius, times the actual velocity dispersion at this radius squared times radius itself, dr. So, and we have this thing that we call the anisotropy parameter beta, which is defined as this thing here, the velocities in one direction in spherical coordinates times the other direction in spherical coordinates times the velocity dispersion, or divided by the velocity dispersion at a given radius. And it is defined in such a way that for a pure rotation of the galaxy, like if the galaxy was rotating as a rigid body or just only rotating without any kind of thermal motion, then you will get an anisotropy parameter of -infinity. If you have completely isotropic velocities, that means that at any given point, on average, you will find the velocities being the same, or the average velocities being the same from all directions, then you have a zero. And for purely radial velocities, you will get an anisotropy parameter of 1. And editing Emil here. I forgot to say that once we have this equation, of course, and once we have the anisotropy parameter kind of nailed down, what we then need to do is to deproject the projected density or density profile, surface density profile that we get in order to find the actual spatial mass profile. This is something that is rather difficult to do, and we have to do something called inversion. The book talks about what is called Abel inversion in equation 526, where you can go and look at that. It's not something we're going to actually do. You need to know that this is a thing that happens, but not something you will be asked to do in lectures or anything. The book also, a little bit further down, talks a little bit about the mass in anisotropy degeneracy, which I haven't included here. It basically shows that anisotropy can masquerade as mass and vice versa. There is a degeneracy between the two that can be kind of difficult to separate. So there are quite a few challenges to this method, but it's also very powerful if we can get past these challenges. So going back to our observations, our integral field spectroscopy observations from before, I guess you can at this point imagine that we can use these velocities and velocity dispersions mainly to insert into this function here, and that way we can map the velocity dispersions, and that way also map the mass as a function of radius, again assuming spherical symmetry. And clearly these are not perfect spheres, so this is still under some kind of very simplifying assumption, but still more detailed and much less simplified than it was with the virial theorem. Another method we can use to map the mass distribution is from X-rays, from hot X-ray gas in these galaxies. As I talked about in the last lecture, the ISM in early type galaxies is overwhelmingly dominated by ionized and very hot gas, like we're talking 10 to the 6 to 10 to the 8 Kelvin compared to the much colder gas in star-forming galaxies. And so we also know that just like the emission from 21 centimeters, X-ray emission is also optically thin. So we can, if we can find a relation between the luminosity in X-rays of a gas and its mass, then we can use the measured flux of X-rays to directly infer the gas mass in the system that we are observing. And so if we're looking at this hot gas at temperatures that are larger than about 10 to the 7 Kelvin, the emission from these galaxies is dominated by, again, optically thin, so-called free radiation. Free radiation means that this radiation comes from electrons that are ionized unbound to atoms both before and after the emission of this, right? So bound radiation is the radiation between two bound levels in an atom or a molecule. Bound free radiation is recombination radiation, where it starts in a free state and ends up in a bound energy state inside an atom. And free radiation is radiation that comes from an electron or potentially an ion, like a positive ion, that is that is ionized both before and after this emission. This free emission is called Bremsstrahlung from German, which means braking radiation. And I guess you have all seen it in optical lights from a synchrotron, as I believe I have talked about before. But at the temperatures of this gas, 10 to the 7 Kelvin or more, this is dominated by X-rays. And it has an emissivity that is given by a known function, right? Where here is this is the number density of electrons at a given point. So the emissivity at point X is the density of electrons at this given point times the total density of ions at this given point times this thing here that we call the cooling function, which is at least in part depending on the gas temperature. And at temperatures like the ones we are talking about here, it is actually more or less only dependent on the gas temperature. Here is an example of various X-ray cooling functions. This is as far back as 2002. I believe the field has moved a little bit since then, but you can see here that they follow the same basic shape, but there is also some quite significant variation between these various cooling functions. And so if we map the surface brightness and the temperature, we can derive the gas mass density profile. Assuming hydrostatic equilibrium and the ideal gas law, we can get this function here. And it is, as you can see, again, derived in the book. But we get this function here, which, as we can see, depends on a number of constants, plus the change in the steepness in the change of gas density and the steepness in the change of temperature. And these are things that we can map observationally from the X-ray gas. That's why it is so useful to us that we have this mass. Expressed in terms of things that are relatively reasonably easy to observe with X-ray gas. And again, m of r is the total mass contained within the radius r, because this all comes down to Newton's shell theorem again. And again, this means that we will be assuming spherical symmetry. So again, some level of simplifying assumptions, but still It is an independent way of measuring it from the stellar dynamics one. And so if we can get these two to agree, then that means we probably have a pretty good handle on the mass distribution inside this given galaxy. And this was the end of part A. This was a little bit long and rambling. I apologize for that, but thank you for staying with me, and I will see you in the next one.